So it says recall this data that was presented at the beginning of this chapter. The explanatory variable is the high temperature for the day in degrees Fahrenheit, and the response is the variable number of visitors to a water park. Okay, so we need to, because we have this data, we need to go right to Desmos. And we're going to plug it on in. I think you guys are starting to get pretty good at Desmos. I mean, I'm like having to help you less and less, which is great. So nice thing is, I'm pretty sure the cell phone's here to stay. And so I think Desmos might be around. So maybe you use it later in other classes. It's like, nope, start. We're just going to use ChatGPT. Gotcha. $92, $88, $90. $80 is the last one. All right. Then 485. Oops. 534. 601. 541. 197. 656. 600. 534. 587. And 478. All right. So a couple of you still on Desmos, so you're like, I don't see my data. Remember, you hit this little magnifying glass, and it'll zoom it to fit. So that looks like a pretty nice representation. So the higher the temperature, the more people that show up to our place. It says find the correlation. So you get on the next line. So remember, it's y1. Then you have to use the tilde, mx1 plus b. Somebody asked, they couldn't find tilde on their thing. So notice on tilde, if I was using this on my phone, if you hit the ABC, it's this very bottom. It's the very bottom one here. So I'm always happy to give you guys a response to it and help you out. Okay, so the correlation is just the R value because we're dealing with straight lines. We don't deal with the R squared. So we have 0.9373. So that's like getting a 93.73% on a test. So that's pretty darn good. Interpret this correlation. So a couple of you missed this on the quiz. You're interpreting correlation as you need to put like a big paragraph with it. Also, I'm looking for on this type of problem is it's strong positive. It's got a positive slope. 0.93 is definitely going to give us strong, so strong positive. Write an equation of the regression equation. So our regression equation is basically this. If you needed to write this, y equals 12.1x minus 523.22. Okay, so you just take the m and the b and plug them into the m and b, change the equal. You don't have to go with the y1 and the x1. Hey, what did we call it when we did this? What did we call that? What? Hey. So why do I do a y hat? What does that mean to the reader if we're going to use y hat? Not change y. Not that I'm adding heat, like in chemistry, sometimes use a little triangle. So if you see the y hat, if you see a y with that little upside down V on top of it, this is, we're going to be making predictions with it. It's the equation we're dealing with for predictions. Okay? So my equation of this, I have to toggle back and forth because I can't remember because I'm not that bright. 12.1 minus 523.2. Okay. So, all right. So they want us to predict. So that's our equation we use for prediction. It actually might be written like this in true statistics. You might have something like this. Okay. Friends, I don't care if you write it in slope-intercept form, that's y equals mx plus b, or you write it in the statistics way. Just realize if it's written in the statistics way, the slope is always attached to the x. So it's just writing it, flip-flopping it. So it says predict the number of visitors to the water park on a day which the high temperature is 75 degrees. So what we can do, we can work hard and we can sub 75 in right there and do the math, or, okay, watch this. A little too much side conversation. Watch this. 75 degrees. Is that the x or the y value?
Probably X.
X, okay? X equals 75, agree? X equals 75. Now, this doesn't happen on the graphing calculator, but Desmos is pretty sweet. So watch this, ready? X equals 75. It draws me a vertical line. That vertical line, the Texas Instruments doesn't do that, but watch this, ready? You can either try and plug that in, or you could say, if it's 75 degrees, we're anticipating roughly 388 people that come to the pool. Okay, you just look at the intersection, and that's pretty cool that Desmos allows vertical lines. I don't know why TI hasn't figured it out. Yeah, they might be. And then predict the number of visitors to this water park on a day that's 95 degrees. Oh, okay. Well, I can do this now. X equals 95. And then I got a blue vertical line. So if it's 95 degrees, I'm going to have 630 people there. If it's 75 degrees, I have 387. Does it make more sense at a water park? Hotter the day, the more people? Seems like a legit thing to do. Okay, let's see. All right. Now, I want to cover this before I go much further. Is the 75 degree, is the red line within my data? Meaning, is there data points to the left of it, to the right of it?
Yeah.
Is the blue vertical line within my data? Meaning, are there data points to the left and to the right?
Yeah.
Yeah, so both of those are called interpolation. Interpolation you can trust. When it's outside your data set, it's called extrapolation, and we said it's not to be trusted. And of course, your science teacher's like, oh, he doesn't know what he's talking about. He's a crazy old man. And that's true, but I'm just saying what statistics is. So to what extent do I trust the predictions based on this regression equation? Okay, I can word this a couple of ways. I have a strong positive correlation. I have a correlation of 0.93, which is very close to 1. So I feel very good about these predictions, especially because it is within our data set. It's acceptable to say that. So if you ran this water park and you kept collecting data and you noted how hot it was, the high temperature of the day, and how many tickets you sold to get into the park, and you kept running the data, you might be able to say, you know, hey, tomorrow's going to be this particular temperature, so we could predict about this many people. So we need to make sure we have this many lifeguards, this many people to clean up stuff, this many people to make sure the chemicals are good in the pool. Okay, those are all things that someone might do. Okay, so then there's one that says predict the temperature when it's 106. Okay, I can do that. I can say x equals 106. It becomes this green line. So when it's 106, based on our model, we should have about 764 customers. People are swimming. And then why? Explain why you should not trust this prediction. Namely, you only have to say one thing. Extrapolation, okay? Extrapolation is not to be trusted. Now, is this a pretty good data model for this pool? I think that people might be able to get away with it, saying, you know, it's going to be 106, and you're like, dude, my data doesn't show anything outside of that. And they're like, ah, it's okay. Well, then it becomes the pool manager's fault that they had too many lifeguards because it maybe didn't get as many people on that day as you thought. But again, it's extrapolation. Extrapolation is not to be trusted. Okay, it's not, you know, and unfortunately, corporations do it all the time. They extrapolate and then they become wrong, and then they start doing the blame game on everybody here and there. Okay. Hey friends, does that page one, that 2-4 make sense? Do you feel comfortable with how I've gone through it? Okay, let's flip the page over to the back side, or the dark side. Here we go. All right. All right. It says on the back side, what page is that? One something? What page are we on? 148. Okay. It says consider the scatter plot in the regression shown. Okay. Explain the relationship that this scatter plot is exploring. Well, it's what is the Y value? Oh, the murder rate versus the burglary rate? Burglary. Okay, so it seems that if the murder rate goes up, so does burglary. Oh boy. What is the explanatory value? That's the X value, which is burglary. Response is murder rate. Estimate that value of R. Okay, does anyone feel that R value is very close to 1?
No.
No, I would say it's a weak, or even maybe you could classify as moderate, positive. So it's weak or moderate, positive, because it would have a positive slope. Explain, you know, there's a positive association between burglary rate and homicide. Okay, so if I estimated my R value, I would probably put it in the category of 0.4, 0.5 positive. Okay, how do we know there's a positive association? Well, our slope to our line would be positive. As I go to the right on my graph is increasing. And then make an arrow pointing to the data point that represents a city with unusually high burglary rate and low homicide rate. Okay. So I could do this. Make an arrow. I don't know. This might be a good one to point to. Large burglary, but it's underneath our line of best fit, so it doesn't quite fit our model. Okay? So is that the only correct answer? There's others that you could say would be correct. Okay? And then move our way down. Let's see. Make an arrow pointing to the data point that represents a city with an unusually high homicide rate, but unusually low burglar rate. Okay. So high murder rate, and it's not as high. It should have been further to the right, but that's just a couple things to do. I mean, it's just there's not always 100% right question or right answer to that. And then, does the regression equation fit those data points very well? So the ones that we had pointed to, I don't think that our line of best fit fits it well. Explain why you should not trust this regression model to predict the number of burglaries in a city with 40 homicides. Well, 40. So we're looking at 40 homicides. Oh. So they said 40 homicides, which is here. All right. So when you are making a y hat prediction, okay, when your equation is y hat equals mx plus b, okay, you can plug in your explanatory to predict. Don't plug in your y to predict. So I can't take my response and predict to make a prediction. I can't go like this. I can't do that. Okay? Actually, this would go way out here because this line should keep going and then come down this way. But it is really bad math to use the response variable to make a prediction based on the x, even if it is interpolation versus extrapolation. Okay? So that's just a couple of things to keep in mind. So don't use the response variable to make a prediction. And let's go to this page. Let's get rid of this. All right, 2-5. 2-5. The slope of the y-intercepts. Okay, around the world of algebra, you learn that the relationship between a slope of a line and the visual properties of a line, and we need to bring those concepts forward. Okay, so when the slope of a regression line is positive, the line is rising, there is a positive association between the variables. Okay, we've already talked about this. A positive slope has a positive association. When the slope is negative, the line is falling. There's a negative association between the variables. So as you go to the right, the graph is decreasing when you have a negative slope. When the slope is 0, this line is horizontal. There's no association between the variables in the scatter plot with no overall rising or falling. So if you plotted all your data points and then made a horizontal line, you don't have an association. And then an undefined slope is a vertical, and it's impossible to get a linear regression because your linear regression needs both an explanatory and a response, or an x and a y value. If you have a vertical line, you only have an x value, you don't have a y value that corresponds to that. So if all your data made a vertical line, that's bad. The correlation R and the slope of the regression line must share the same sign. So it's positive association, it's got to be positive slope, negative association, negative slope. Okay, the slope of a regression line measures something important. It is predicted the amount of response variable will increase when the explanatory variables increase by a single unit. Consider the linear regression model that they have. So it says predicted sales, 640 plus 12 times the number of ads. So from algebra, remember that the slope is the change in the y over the change in x. So if I deal with this, this means that the slope of the regression line above 12 can be represented as 12 over 1, which leads to a change in the y direction. Delta y means it's changed vertically in the y direction. In the change in the x direction, essentially this means that you increase 12 units for each 1 unit that x increases. Okay, now in statistics, my friends, and this is backwards from algebra. In algebra, we like to have slope staying as a fraction. Agree? So let's say you have 3/4 as a slope. That means vertically it changes 3 for every horizontal 4. In statistics, you want to keep your slope. You really do want to keep your slope as a number or a decimal. That way, if you make it as a number, if it's a true number, if it's just 5, then you make it 5 over 1. But if you made it like 0.75, that'd be 0.75 over 1. So you want to make sure you keep your x variable as 1 unit to make more sense of what you're dealing with. The predicted sales will increase $12 for each additional ad that is placed. Another way of phrasing this is the sale increases at a rate of $12 per ad. When the slope is negative, it predicts a decrease in the response variable with each increase of 1, the explanatory variable. If, for instance, the slope of the regression had been negative 12 instead of positive 12, the interpretation would have been the predicted sales would decrease $12 for each additional ad that is placed. And you shouldn't be putting ads if you had that kind of situation take place. Okay, so slope, don't put as a fraction. Make your fraction a decimal. When you make your fraction a decimal, that means you can put your decimal over 1. That means your x variable, which is your explanatory, will only increase 1. You flip the page. Says the y-intercept is simply a value of the response variable that is associated with the value of 0 in the explanatory. So sometimes the y-intercept doesn't make sense in the context of the problem. I think on the pool problem, if we look at that pool problem, my b value is negative 523. So that means when it's 0 degrees outside, you have negative 523 people that show up to the pool. That doesn't really make sense. Okay, they might be showing up to the pool for a different reason if it's 0. They might be ice skating that day. Maybe they're in their bathing suit though. That's some chilly stuff. In the previous example, the y-intercept is 640. And it can be interpreted when 0 ads are used. They will have 640 in sales. That was from the previous page. Beware, the y-intercept often produces highly unusual, even impossible interpretations. This is because the y-intercept is extrapolation. Okay? A lot of times that y-intercept is very uncommon that you're going to have a data, a point that is going to be at 0 comma something. And if that's the case, it becomes extrapolation, and extrapolation shouldn't be trusted. Okay? Average strikeouts per game, they have it listed as negative 18.3 plus 0.2685 times the average speed of the fastball. So in this case, that basically means if somebody threw a 0 per hour fastball, that's pretty slow, isn't it? That you'd have negative 18.3 strikeouts. That doesn't work that way. So again, because it's extrapolation, it doesn't always make sense. The premise of this linear regression equation is, in baseball, the speed at which a pitcher throws a fastball may be a predictor of the average number of strikeouts that he will throw per game. This makes sense. The faster the baseball is flying towards you, the harder it is to hit. The interpretation of the slope makes sense. Each increase of 1 mile per hour, the speed of the fastball predicts 0.2685 more strikeouts. However, the interpretation of the y-intercept creates a silly result. Pitcher throwing 0 miles per hour will have negative 18.3 strikeouts per game. Okay, and again, that doesn't make sense. The correct interpretation should not be altered. So should not be altered simply to make the result plausible. I think we can agree a pitcher throwing 0 miles per hour will not be allowed to pitch for very long. I mean, that's guy just holding the ball. Oh, strike 1, 2, 3. Oh, look, I was just holding the ball the whole time. And it is impossible for a pitcher to get negative amount of strikeouts in a game. So remember, though the y-intercept will often produce ridiculous interpretations because prime examples of extrapolation using a value for the explanatory variable that is either low or higher than the explanatory values is used to create a regression model. Okay, so again, where it crosses the y-axis is often a funny place, kind of a silly interpretation. I mean, that one with the water park that we still have up on the board. If it's 0 degrees, how am I going to have negative 523 people show up to the pool? It just doesn't happen. It's like you got their ghosts there or something. I don't know. So that's about all I got for you. So what do we say? We'll do 2-5. So 2-5 is what you can do. I think I actually gave one of the answers right here, so you have an answer. So you have the rest of the time to work on that. I'll stop my recording. Hey, what's Friday?